So let us start the new chapter, again a very important chapter as per as JEE Advanced and JEE Main syllabus goes, that is electrochemistry. Now again we are going to do the chapter in the same pattern in which we did solutions as well as chemical kinetics. Okay. So for initially 2 or 3 lectures we will discuss all the theory in detail. We will understand the different kind of electrochemical series, we will understand the different kind of electrochemical cells, and then we will go on to solve difficult level questions. Again this chapter, if you do a lot of theoretical reading, theoretical research and have the idea of all the concepts, then problem solving in this chapter is again very easy. So this is not a difficult chapter as cited by many, but this has a very good amount of theory that has to be done properly. You have to make very crisp notes and you have to have a good reading. Okay. So let us start the lecture. Okay. So I hope you are having a copy and a pen with you so that you can take out the important points which are being delivered in the lecture. Okay. So you might have studied this in the redox chapter as well. We talked about electrode potential. Okay. So basically today's lecture will be focused on electrode potential, what is standard electrode potential, what is reduction potential, what is oxidation potential, and how they are used to build a cell or a battery. Okay. So now basically electrochemistry, okay, it is the branch of chemistry that deals with the study of production of electricity from chemical energy released during spontaneous redox reaction. Okay. So this is a very common observation that you might have made in your home also, like if you see a battery you can draw current from the battery. Okay. If you look at when the power goes off, we have a sulfuric acid battery in our home that is connected to an inverter, so we can have the power from there as well. So basically these are the devices that produces electrical energy. A pencil battery is there, okay, the cell in the watches, even the battery that is connected to the inverter gives us current. So that is basically known as a galvanic cell. Okay. So electrochemistry majorly deals with the production of electricity from chemical energy. Okay. So there is some chemical reaction happening inside a lead storage battery or inside the pencil battery. Okay. There is some chemical reaction going on and that chemical reaction is a redox one. So in any of the pencil cells there is a redox reaction that is going on. Okay. So the chemical energy liberated from it can be converted into electrical energy. Okay. And that is what studied under the branch of electrochemistry, or vice versa. Okay. You might have studied about the electrolytic cell, that we are passing electricity through a solution of an electrolyte and we decompose that electrolyte into cation and anion. The cation migrates toward one electrode and the anion migrates toward the other electrode. Okay. So electrochemistry is the branch of chemistry that deals with the study of production of electricity from chemical energy, okay, released during spontaneous redox reaction, okay, and the use of electrical energy to bring about a non-spontaneous chemical transformation is studied under the electrochemistry. So we are talking about, okay, so we are talking about a electrochemical cell. Okay, so we are talking about an electrochemical cell. Okay, so this cell basically converts, okay, so this converts chemical energy, okay, this converts chemical energy into electrical energy. Okay, so there is a spontaneous redox reaction that is happening. Okay, so there is a spontaneous redox reaction that is happening. Okay, so there is a spontaneous redox reaction that is happening, that is a chemical energy is released that is converted into electrical energy. Okay, so the second type of cell is the electrolytic cell. Okay, so if you look at the electrolytic cell, okay, now in this current is produced. Okay, now in this current is produced, but in this cell we use the current or we use the electrical energy to convert it into a chemical energy. Okay, so we convert, so this is conversion of electrical energy into chemical energy. So in electrochemistry we are going to discuss these two important cells, that is electrolytic cell and a galvanic cell. So we are going to discuss them in detail. Initially we will start with the electrochemical cell. We will understand how electrochemical cell works, what are the common type of electrochemical cells that are available and what are standard potentials. Okay. So basically electrochemistry deals with these two branches, that is conversion of chemical energy into electrical energy, that is done through a electrochemical cell, and the conversion of electrical energy into chemical energy, that is done through a electrolytic cell, where we pass electricity to any aqueous solution and we cause the breaking of that particular compound, and a non-spontaneous reaction can also take place through this. Okay, so that's what it is written over here. Okay, hope this is clear to you. Okay, so let us start with the first concept, that is the concept of electrode potential. Okay, now let us first understand what is electrode potential and how it is going to be useful in the upcoming sessions. Okay, so let me just consider, okay, let us suppose that we are having a container. Okay, this you might have done in your Redox chapter as well, but we are going to discuss in detail. Okay, so what we are doing, we are taking a solution. Okay, we are taking a solution, say containing a metal ion. Okay, so what we are doing, we are taking a solution, okay, containing a metal ion. That means we have dissolved some electrolyte in that solution which will give us the metal ion. Okay, suppose we wanted to have, say, copper 2+ in the solution. So what we'll do, we'll dissolve copper sulfate in water, so we'll have copper 2+. So anion is also present, but I'm just like denoting here the metal ion that is present. Okay, so what we are doing is, we are just dipping a, okay, we are taking a metal rod. Okay, so we are taking a metal rod, so this is a metal rod. Okay, so this is a metal M. So we are dipping a metal rod in its own aqueous solution containing the ion. Okay, so metal rod is basically dipped into the solution containing the ion. Okay, so metal rod is M and the aqueous form has the cationic form of this metal, that is Mn+. Okay, N is the general oxidation state that this metal can have. Okay, or the valency that this metal can have. Okay, so we are talking about a metal rod. Okay, we have dipped a metal in the aqueous solution, okay, containing the metal ion. So when we take this as a system, so now three things can happen over here. Okay, hope this is clear to you. So what we are doing over here, first we are taking a metal rod, we are dipping that metal rod in the aqueous solution containing the metal ion. Okay, the same metal ion that is present in the same metal that is present as the rod. Okay, so we are dipping a metal rod into an aqueous solution containing the metal ion. So now here three things can happen. Okay, so before understanding all the cases, let us understand what are the two important parameters that we need to know before going into the detail. Okay, so the first point that you should understand over is the tendency of a metal, okay, the tendency of the metal to pass into the solution as ion is measured by the solution pressure. So I am telling what can happen over here, the metal, okay, can get oxidized and it can get converted into metal ion. Okay, so the metal get oxidized and it gets converted into the metal ion, and this metal ion goes into the solution. Okay, so this is a metal, okay, this will get oxidized, so the metal ion which is produced will go into the solution and the electron will remain at the rod. So this tendency of metal to get oxidized into metal ion, okay, and pass into the solution is measured by solution pressure. Okay, so solution pressure will tell us the tendency of a metal to pass into the solution as ions. Okay, the second important is osmotic pressure. So I will just erase this if you are not able to see this. So this is basically our metal rod. Okay, so the metal has the tendency to go into the solution as metal ion. That would be measured by solution pressure. Similarly, the metal ions which is present inside the solution can take up the electrons or can get reduced and convert into metal. Okay, so if metal ion gets reduced, so it will take up the n electrons, okay, from the solution and it will change into metal. Okay, and this will get deposit on this rod. So this metal ion that is present inside the solution has the tendency to gain electron and get converted into the metal, and this metal will get deposited on the rod. So this metal ion has the tendency to get deposited at the metal rod or the electrode. Okay, now this is measured in terms of osmotic pressure. So there are two important terms that you should understand over here. Is first is the tendency of metal to get oxidized and change into metal ion. Now that metal ion can pass into the solution. Okay, so this metal can get oxidized and it can pass into the solution as metal ions. Okay, so this tendency of metal, okay, passing into the solution in the form of ion is measured by solution pressure. Okay, hope this is clear to you. Now the metal ion that is present in the solution has the tendency to gain electron and get reduced into metal. The metal form can go and deposit at the electrode or at the metal rod. So the ions in the solution have the tendency to go and get deposited at the electrode. This tendency is measured by the osmotic pressure. Okay, so hope this is clear to you. So when you dip a metal rod in its aqueous solution containing the common ion, okay, when you dip a metal in the aqueous solution containing the metal ion in the solution, now there are two things that can happen. Either this metal can get oxidized and change into metal ion and pass into the solution. Okay, that is measured by solution pressure. The second thing that can happen is the metal ion that is present inside the solution can get reduced and get converted into metal and get deposited at the rod. So this tendency of metal ion to get deposited at the rod in the form of metal is measured by osmotic pressure. So depending upon which is greater, okay, if suppose solution pressure is greater than osmotic pressure, then the metal will get oxidized and the metal ion will come into the solution. If the osmotic pressure is more, then we will say that the metal ion will get reduced and metal will be deposited at the metal rod. Okay, so these are the two basic concepts that you should know over here before we understand the concept of electrode potential. Okay, so we are having now three cases. Okay, the case 1 would be, okay, case 1 in this case would be if osmotic pressure is greater than, or the first case is, rather let us select if solution pressure is greater than osmotic pressure. Okay, so let us take this condition and understand what is going to happen. So we are again having a, okay, solution containing a metal ion. Okay, and into this metal ion, its metal is dipped. Okay, in case you have any problem when I am doing the theory, you can just write in the chat box so that I can revisit it so that the concepts are understood to you, because this is actually very important. If you are through with the theory, if you know the theory in detail, then there would be no problem in solving the questions. The questions that come in this chapter are definitely, you can consider it to be a good level questions. Okay, so this chapter is basically considered as one of the most important and a tricky and a difficult chapter. But if you are clear with all the theory, the different aspect of the theory, then believe me, this is not difficult at all. Okay, so what we have done over here is we have dipped this metal. Okay, so we have dipped this metal. Okay, so we have dipped this metal rod in its own ion in the aqueous solution. Okay, now if the solution pressure is more, now we know that solution pressure is the tendency of the metal to pass into the solution as metal ion. So if this passes into the solution, so what will happen over here? So oxidation would take place. Okay, when solution pressure is more, osmotic pressure is less, so the metal would pass from the rod into the solution as ion. So metal would get oxidized into metal ion. Okay, hope this is clear to you. So we'll say that oxidation will happen. Okay, now when this oxidation is happening, the metal is getting oxidized and the metal ion is passing into the solution. So the solution will develop excess positive charge. Okay, because there was already positive charge in the solution along with the negative charge. So consider like this, we are dipping zinc in the zinc rod in the zinc sulfate solution. Okay, so zinc rod is there, it is dipped in the zinc sulfate solution. So this is zinc rod dipped in its own aqueous ion, that is zinc 2 plus. So zinc is dipped in zinc 2 plus, but the solution is also having sulfate ion. So the solution currently is electrically neutral. Now when zinc gets oxidized, when the zinc present on the rod gets oxidized and converts into zinc 2 plus ion, the zinc 2 plus ion will enter into the solution. Okay, therefore the positive charge in the solution will keep on increasing. Okay, so the solution will acquire positive charge in this case. Okay, so we will say that solution acquires positive charge. Okay, hope this is clear to you. So metal is getting oxidized, metal is passing as metal ion in the aqueous solution. The electrons which are liberated, okay, the electrons which is released will remain on the rod itself. Okay, so it will remain on the rod itself. So the rod has the negative charge. So metal acquires positive charge and metal rod or the electrode in this case acquires negative charge. Okay, so when we are dipping a metal into its aqueous solution, if the metal is getting oxidized, okay, the metal will change into metal ion and that will pass into the solution. The solution will become positively charged because positive cation are going into the solution, and the electron which is liberated will remain on the rod. Okay, due to which the metal cation that is in the solution would come near to the rod because of the attraction between positive and negative charge, and it would form a electrical double layer. Okay, so this will form a electrical double layer. After some time what will happen, because there are so many metal ion that is accumulated around the rod, because the rod is having negative charge and the metal cation is having positive charge, so because of the attraction there is a formation of electrical double layer. Now as this electrical double layer like gets attracted to the metal, so the oxidation of further metal would be inhibited because there is already positive charge just outside the rod which will keep repelling the metal ion that is coming from the rod. So the oxidation would stop at certain point. Okay, we will say that something like an equilibrium has been achieved. So when you dip a metal rod in its aqueous solution, if the osmotic pressure, if the solution pressure is greater than osmotic pressure, metal will have tendency to get oxidized. Metal will get oxidized and pass into the solution as metal cation. Okay, and the electron would remain on the rod. Therefore the rod or the metal electrode or the metal electrode would acquire negative charge. Solution will have a positive charge, so there would be electrical double layer set up between the rod and the solution. Okay, due to this electrical double layer, there would be a potential that is set up between the rod and its aqueous solution. Okay, so this potential that is set up between the metal and the metal ion in the aqueous solution is known as electrode potential. Okay, hope this is clear to you. Now if we consider case 2, okay, if osmotic pressure is greater than solution pressure. Okay, so what would happen in this case? So suppose we are having a metal rod and say we are having a solution in it, okay, containing a, say, a metal ion, okay, and we are dipping the metal rod in it. Okay, so we have dipped a metal rod in it. Just let me just draw it first. Okay, so we have again dipped a metal rod, okay, in its aqueous solution, okay, in the solution containing the ion, okay, of that metal. So if osmotic pressure is more, now what is osmotic pressure? The tendency of the metal ion to get reduced and get deposited at the metal rod. Okay, so if this tendency is more, then we'll say that reduction of metal ion is happening. Okay, so the reduction of metal ion in the solution is happening and it will get reduced into metal. Now this metal formed would get deposited at the electrode. Okay, so when this metal ion from the solution goes out and get converted into the metal and get deposited at the metal, so we'll say that the number of positive cation in the solution would decrease. Okay, because suppose if there are say 20 cation, suppose we have dipped zinc in zinc sulfate solution. So suppose there are 20 zinc 2 plus ion and 20 sulfate ion, because the solution is electrically neutral. Now out of those 20 zinc 2 plus, let us assume that some zinc 2 plus gets reduced and changes into zinc and it gets deposited at the rod. So the number of positive charge, okay, so the number of positive charge ions in the solution would decrease, so the number of anions in the solution would increase. So this would lead to the formation of negative charge in the solution. Okay, so we'll say that the solution acquires negative charge. Okay, the solution acquires negative charge. Okay, hope this is clear to you. And the rod will acquire positive charge. Okay, now again you see there is a positive charge on the rod, there is negative charge in the solution. So these negative charge will get attracted to the positive charge and it would form a double layer. Okay, it will form an electrical layer, which is electrical double layer, okay, near the rod. Okay, so this will form, okay, a double layer near the rod. So we'll say that there is a potential difference set up between the rod and the solution. Okay, so this potential difference set up between the solution containing the ion and the metal, okay, is known as electrode potential. Okay, so in this case you can see that oxidation is happening. Okay, when solution pressure is greater than osmotic pressure, we'll say that oxidation is happening, and if osmotic pressure is greater than solution pressure, we'll say that reduction is happening. So in this case, solution will acquire negative charge and metal rod or the electrode acquires positive charge. Okay, so there is an electrical layer that is set up near the rod, okay, which leads to the development of a potential difference, due to which a potential is set up between the rod and its solution, which is known as electrode potential. So now you might have understood the concept of electrode potential. Whenever you are dipping a rod in its solution, okay, containing the ion, okay, you are dipping a rod in a solution containing the ion that is made up of metal only, okay, so there would be a potential difference between the rod and the solution. Okay, so there is a potential difference between the rod and the solution. This potential difference is known as electrode potential. Okay, so case 3 would be when both osmotic pressure is equal to solution pressure. Okay, so in this case we will say that metal has the tendency to go into the solution as metal ion, and similarly metal ion has the tendency to get reduced and get deposited as metal on the rod. So in this case we will say that neither oxidation nor reduction would happen. Okay, so I hope this is clear to you. So I'll just quickly revisit what I am saying. Now when I have just taken a metal rod and I have dipped in a solution containing the metal ion. Okay, now there are two things that can happen. The metal is having a tendency to get oxidized, okay, and the metal ion is having the tendency to get reduced. Okay, so if the tendency of metal ion, if the tendency of metal to get oxidized is more than the tendency of metal ion to get reduced, so we'll say that in that case the metal will undergo oxidation. So the metal present in the metal rod would undergo oxidation, it would change into metal ion, and that metal ion would enter into the solution. Now when this metal ion enters into the solution will acquire positive charge. The electron that was liberated would be sitting at the metal, so there would be a potential difference between the rod and the solution. An electrical double layer would be set up near the metal surface that would lead to the development of a potential which is called as electrode potential. Okay. Now if you are taking the metal rod, dipping in the solution containing the metal ion, now again there are two things that can happen. Okay, the metal ion has the tendency to get reduced, the metal has the tendency to get oxidized. If the tendency of metal ion to get reduced into metal is more than the tendency of metal to get oxidized, so what will happen in that case? Metal ion will get reduced, so metal ion will take up the electron and get reduced into the metal, which will get deposited at the electrode or at the metal. Okay, so when reduction is happening, we will say that the positive charge in the solution is decreasing because some of the cations are getting reduced. So the solution will acquire negative charge, rod will have a positive charge. So there would be a electrical double layer set up near the electrode, due to which we will say that a potential has been set up. Now due to the setup of this potential, okay, there would be a potential difference which is known as electrode potential. So electrode potential is basically the potential developed when a metal is dipped in its solution containing the metal ion. Okay, if both osmotic pressure and solution pressure is same, we will say that there is an equal tendency of metal to get oxidized and the metal ion to get reduced. In that case, nothing would happen. Okay, hope this is clear to you. I hope you have taken a snapshot of this as well now. Okay, so we will say that the tendency of an electrode to lose or gain electron when it is in contact with its own ion in solution is called as electrode potential. Okay, so we will define electrode potential as the potential difference, okay, set up between the potential difference set up between the metal, okay, the metal rod and the solution containing metal ion. Okay, so this is called as electrode potential. Okay, so we also define this as the tendency of an electrode to gain or lose electron when it is in contact with its own ion in solution is called as electrode potential. Okay, so hope this is clear to you. Okay, so we defined a standard electrode potential. Okay, so standard electrode potential is the potential measured at standard condition. Okay, so whenever you are measuring the electrode potential under standard conditions, when the temperature is 298 Kelvin, okay, standard condition and STP conditions are different. STP is standard temperature pressure. Standard condition is basically the condition where temperature is 298 Kelvin, pressure is 1 atm. Okay, So if you measure this electrode potential under standard conditions when temperature is 298 Kelvin, okay, pressure is 1 atm and the concentration of all the ions is 1 molar, okay, or the activity of all the species is 1, then the potential is called as standard electrode potential, which is represented by E naught. Okay. So standard electrode potential is the potential, okay, is the electrode potential measured under standard condition. Standard condition is when temperature is 298 Kelvin, pressure is 1 atm, concentration is 1 molar and activity of all these species is unity. Okay. So that is not written over here, but it means that concentration, if there are gases involved, their partial pressure has to be equal to 1. So activity of all the ions, okay, gases is 1. So the electrode potential measured under standard condition is known as standard electrode potential. Okay. So let me just take an example to make you understand this. Suppose we are talking about a oxidation reaction. Okay. Now I will take the known cases. So let us consider that we are having zinc. Okay. So zinc has the tendency to get oxidized. So when you dip a zinc into the aqueous solution containing zinc ion, okay, so there are two things that can happen. Zinc can get oxidized into zinc 2 plus ion. Also zinc 2 plus ion in the solution can get reduced into zinc. Okay, so we have to check which factor is more dominating or which tendency is more to happen. Okay, which tendency is more to happen. So in this case, zinc getting oxidized into zinc 2 plus is having the preference, okay, because the tendency of zinc to get oxidized is more than that of zinc 2 plus to get reduced. So overall what would be happening in this case? Zinc would get oxidized into zinc 2 plus and it will give us 2 electron. Okay, hope this is clear to you. Now this is basically representing an oxidation reaction. We are losing electrons. So this is basically a oxidation reaction. So we will write its oxidation potential. Okay. So if we want to write the standard oxidation potential, it would be written by E naught, not represent that all the conditions, okay, are standard ones. So E naught OP is equal to plus 0.74 volt. Okay. So oxidation potential of zinc is 0.74, or we can also write, okay, zinc is getting converted into zinc 2 plus, so this is equal to 0.74. Okay, so this is basically showing the oxidation, zinc changing into zinc 2 plus. We have separated with a bar because the phase of both of them is different. One is solid and one is in the aqueous solution. So that's why we are showing a bar over here, okay, which indicates that both of them are in different phases. So this is how we write the oxidation potential. Okay, so the oxidation reactions, we'll write their oxidation potential. Okay, so oxidation potential is basically of zinc is 0.74. Now if you want to reverse the reaction, okay, so if we are reversing the reaction, okay, so if we are reversing the reaction, so this would basically become zinc 2 plus aqueous plus 2 electron changing into zinc solid. Okay, so what is happening in this case? This is reduction of zinc 2 plus. So we'll write E naught, that is standard, okay, reduction potential of zinc 2 plus ion, because zinc 2 plus ion is getting reduced in this case. Now because we have reversed this reaction, so the standard EMF, okay, standard electrode potential, okay, oxidation potential was plus 0.74, so the reduction potential would become minus 0.74 volt. Okay, so I can also write this as E naught zinc 2 plus changing into zinc, this is minus 0.74 volt. Okay, so when we are dipping a metal in its aqueous solution, we'll say that a potential has been set up which is called as electrode potential. If oxidation is happening, we can write its oxidation potential. If reduction is happening, we can write its reduction potential. Okay, so oxidation potential will represent the tendency of a metal to get oxidized or any substance to get oxidized. Reduction potential, standard reduction potential would indicate the tendency of a substance to get reduced. Okay, so I hope this is clear to you and I hope you are clear with the notation. Okay, zinc 2 plus means oxidation, bar means both of them are different phases. zinc 2 plus changing into zinc, again both of them are in different phases, so they will be separated by bar. So we'll say that standard reduction potential is always negative of standard oxidation potential of any substance. Okay, hope this is clear to you. Okay. Now, let us just understand the significance of standard electrode potential. So, few points which we have to remember before we jump onto the important theory in this chapter. The first thing is, more is the positive reduction, okay, more is the positive reduction potential, more would be the tendency of the substance to get reduced. Okay, hope this is clear to you. So, more is the value of reduction potential, more would be the tendency of the substance to get reduced. Okay, so reduction potential, if reduction potential is positive, it means that reduction is spontaneous. More is the value of reduction potential, more positive is the value of reduction potential, more is the tendency to get reduced. Okay, similarly we will say that more is the positive oxidation potential, okay, more would be the tendency, more would be the tendency, okay, more would be the tendency of substance to get oxidized. Okay, let me explain it through an example. Suppose you have been given E naught M2 plus M. Okay, suppose the value is given to you as say minus 0.8 volt. Okay, so what you can infer from this? Okay, so first you have to look at the notation that has been given to you. So here you can see M2 plus is changing into M. So this is reduction because oxidation state is reducing. So you have been given M2 plus aqueous gaining 2 electrons changing into metal. Okay, because this is the reduction potential, because this is a reduction reaction, so the reduction potential has been given to us as 0.8 volt. Okay, now if we want to write the reverse of this reaction, or if we reverse this reaction, so this would become metal solid changing into M2 plus aqueous plus 2 electron. Okay, so this is reduction, reverse of would become oxidation. So the oxidation potential of this would become plus 0.8 volt. Okay, so the reduction potential is minus 0.8, means that the oxidation potential of metal is 0.8. Now, what is the tendency of the metal or the metal ion in the solution to behave as? Okay, so you can clearly see that because the reduction potential is negative, so reduction is not that spontaneous, but oxidation of this is highly spontaneous because oxidation potential is positive. So more is the positive value, more would be the tendency to get oxidized. Okay, or we'll say that, okay, or we can also say that suppose we are having two metals. Okay, suppose we have been given two metals, say the reduction potential of standard reduction potential of a metal A plus. Okay, suppose the standard reduction potential of the metal A2 plus changing into A is suppose minus 0.5 volt. Okay, and say the reduction potential of B2 plus B is minus 0.8 volt. Okay, now you can see that the reduction potential of A2 plus changing into A is minus 0.5 and reduction potential of B2 plus changing into B is minus 0.8. Okay, So what would be the oxidation potential? So oxidation potential of A changing into A2 plus would be 0.5 volt, okay, and the oxidation potential of B changing into B2 plus would be 0.8 volt. Okay, so the question can come, out of 1 and 2, which is likely to undergo oxidation more easily? So we'll say that because oxidation, because we want to talk about oxidation, okay. So we'll say that the tendency of B to get oxidized into B2 plus will be more because its oxidation potential is more. So B will have more tendency to get oxidized, okay. And similarly we can say because B has the more tendency to get oxidized, okay, so B will have less tendency to get reduced. Similarly we'll say that A is having, okay, a good tendency to get oxidized because oxidation potential is positive over here, okay. So we can just direct, by looking at the reduction potential data, we can predict whether the oxidation of the substance or the reduction of the metal ion or the reduction of the other species is happening or not, okay. So just look at the data. So it says that if the oxidation potential is more positive, okay, if the oxidation potential is more positive, then the tendency to get oxidized is more. If the reduction potential is more positive, then the tendency to get reduced is more, okay. So hope this point is clear to you. Okay, so we can say that if we are comparing between, say, two elements, like in this case the reduction potential of both of them was negative, okay. So reduction potential of both of them was negative, A2 plus as well as B2 plus. Oxidation potential of A and B both would be positive. B oxidation potential is more positive, hence the tendency of B to get oxidized would be more than that of A. Now if we want to compare to reduction potential, okay, so we'll ask out of these two which has more tendency to get reduced, okay. So we'll say that the one which is having less negative value is having more tendency to get reduced, okay, because more negative is the reduction potential, lesser would be the tendency to get reduced, okay. So reduction potential has to be positive, so more is the positive reduction potential, more is the tendency to get reduced, okay. But if it is more negative, then it means it will not undergo reduction. So we are saying that if the reduction potential is less negative, okay, so just leave the magnitude, leave the sign for the time being. So if you see this is 0.5, this is 0.8, so the reduction potential is less negative for, okay, I am not considering the sign, okay. So if the reduction potential is less negative, so it will have more tendency to get reduced as compared to the one which is having more negative value, okay. Hope this is clear to you. So significance of standard electrode potential. So standard electrode, through the value of standard electrode potential, we can easily predict whether a substance will undergo oxidation or reduction in a given reaction, okay. So this helps in predicting whether oxidation or a reduction of a substance would be happening in a reaction or not, okay. Predicting oxidizing or reducing agent, we know that the substance which is getting oxidized will act as a reducing agent and the substance which is getting reduced will act as a oxidizing agent. So looking at the value of the electrode potential, we can predict whether oxidation is happening, whether it is acting as a reducing agent or not, okay. Also the third last point that we are going to discuss in detail, we can use the value of the electrode potential in calculating the overall EMF developed in a given cell, okay. Hope this is clear to you, okay. So what I am saying over here is I will just quickly revisit it. So I am saying that if a substance is having more positive reduction potential, okay, if reduction potential value is more and more positive, the tendency to get reduced is more. So that substance would undergo reduction and it would not undergo oxidation. If the oxidation potential is very positive or it is having a positive value and higher is the positive value of the oxidation potential, more would be the tendency to get oxidized, okay. Hope this is clear to you, okay. So we'll say that in general by default or by in general we'll say that standard electrode potential will mean standard reduction potential. If in question you have been written that the standard electrode potential of a particular like substance is say X, so that means it is the standard reduction potential. So if nothing is quoted in the question, it is written standard electrode potential, so we have to consider it as a standard reduction potential. Okay. So just let me take you through some example. Let us consider an example. Suppose we have been given E naught of A2 plus changing into A as say 0.6 volt, okay, E naught A3 plus changing into A as say minus 0.2 volt, and say E naught B2 plus changing into B as say 1 volt. Okay, so we have been given three datas of electrode potential. Now you can see that all of them are a reduction potential. Okay, all of them are reduction potential. A2 plus changing into A, A3 plus changing into A, B2 plus changing into B. Okay, so we can quickly write the reaction. A2 plus, okay, obviously it will be in the aqueous solution because it is an ion. It will take up 2 electron and changing into A. Okay, so this is a reduction reaction. So the potential given is that of reduction. So this is your reduction potential value. A3 plus is taking up 3 electron from the solution and changing into A. Now the reduction potential is given as minus 0.2 volt. Okay, similarly B2 plus is gaining 2 electron and changing into B. Now its reduction potential is given as 1 volt. Okay, I hope this is clear to you. Now the question can ask which substance has maximum tendency, okay, which substance has maximum tendency to get reduced. Okay, so I have already told you now the substance which is having the most positive value of reduction potential will have the most tendency to get reduced, will have the maximum tendency to get reduced. So in this case the reduction potential is maximum for B2 plus. Okay, so B2 plus has the maximum tendency to get reduced. Okay, also this can say that which is the strongest oxidizing agent among the three. Okay, so again we can say that the substance which can easily get, okay, standard strongest oxidizing agent. So we will say that the substance that can, okay, the substance that can easily reduced will act as a strongest oxidizing agent. The substance which can get easily reduced will act as a strongest oxidizing agent. So answer again would be B2 plus. Okay, hope this is clear to you. Third question that it can be asked from this data is which has the maximum tendency to get oxidized. Okay, so let us observe their oxidation potential. Okay, so reduction potential of A2 plus was 0.6. So if you write the reaction in reverse, it would become the oxidation of A. So oxidation potential of A would become in that case minus 0.26. Okay, if you reverse this reaction, A changing into A3 plus, this would become the oxidation potential of A changing into A3 plus, which would be minus 0.2 volt, that is 0.2 volt. Similarly, if you reverse the third reaction, this would be B changing into oxidizing into B2 plus, this would be minus 1 volt. Okay, so you can see that the oxidation potential of A changing into A3 plus is positive. Okay, so it is having the tendency to get oxidized. Okay, so the maximum tendency to get oxidized would be A. Okay, and that to A changing into A3 plus. Okay, so A changing into A3 plus. So in this case, this A will act as the strongest reducing agent. Okay, the substance which is getting oxidized will act as the strongest reducing agent. Okay, the last question that can be asked in this is, arrange them according to their, say, oxidizing character. Okay, so we know that we have to, or their oxidizing power. So we know that the substance which is getting easily reduced will have the maximum oxidizing power. Okay, so we have already said that B2 plus is having the highest tendency to get reduced, so it would be most oxidizing in nature. Now if you consider between A2 plus and A3 plus, the reduction potential of A2 plus is 0.6, which is positive, and the reduction potential of A3 plus is negative. So tendency of A2 plus to get reduced will be more than that of A3 plus. So A2 plus will be the stronger oxidizing agent than A3 plus. Okay, so this would be the answer. Now if you want to arrange them in their reducing power, okay, or in their reducing character, so to act as a reducing agent, they need to undergo oxidation. So the substance which is having the maximum oxidation potential will have the maximum tendency to get oxidized, okay, and will act as the strongest reducing agent. So you can see that the strongest oxidizing, the tendency to get oxidized was maximum for A changing into A3 plus. So reducing character of A changing into A3 plus would be maximum, followed by, okay, now both of them are negative. Okay, A changing into A2 plus, oxidation potential is negative. B changing into B2 plus, oxidation potential is again negative. Now out of these two, the oxidation potential of this is less negative. Okay, you can see the magnitude is 0.6 and this is 1. So the tendency of this to get oxidized will be more than that of B. However, both are having negative value, so their overall tendency to get oxidized is less. But if you compare between these two, okay, A changing into A2 plus and B changing into B2 plus, so the tendency of A getting oxidized into A2 plus which is more than that of B changing into B2 plus. So we will say that A changing into A2 plus would be a stronger reducing agent than B changing into B2 plus. Okay, so this is a very standard question that you can find in JEE mains, BITSAT state level examination. A direct question comes on the thermodynamic data would be given to you, and you have to predict which is the stronger oxidizing agent, which is the stronger reducing agent, which will have more tendency to get oxidized or reduced. Okay, so hope this concept is clear to you. Now what we have done till now is we have just defined electrode potential. Okay, the electrode potential when measured under standard condition, okay, when activity of all the species is 1, the temperature being 298 Kelvin and pressure being 1 atm, then it is called as standard electrode potential. Standard electrode potential by default means standard reduction potential. More is the value, more positive is the value of reduction potential, more is the tendency to get reduced, okay, and more positive is the value of oxidation potential, more is the tendency to get oxidized. Okay, so this is what we have done till now. Now if you look at the electrochemical series, okay, now this you were learning in the form of activity series in your junior classes, but this is basically based on the reduction potential. Okay, so electrochemical series, okay, is basically based on their decreasing value of reduction potential. Okay, so you can see that all these substances are getting reduced and we have written their reduction potential. So we know that this is the positive reduction potential and this is the negative reduction potential. Okay, so the positive reduction potential means that tendency to get reduced is very high, so it will act as a oxidizing agent. Okay, so this is a stronger oxidizing agent. The tendency to get reduced is very less. Okay, so their reduction is not spontaneous, so their oxidation would be spontaneous. Okay, so they would act as a strong reducing agent. Okay, hope this is clear to you how we are writing this. So you have to remember few of the values. Fluorine changing into fluoride ion has the maximum reduction potential. Okay, and the minimum reduction potential is that of lithium minus 3 volt. Okay. Hydrogen reduction potential is 0. H plus taking up 2 electron changing into hydrogen is 0. Okay, we will discuss these cases, few of these cases when we discuss the different types of electrode. So H plus is the reference point. Okay, reduction potential of H plus is 0. Okay, and the species lying above it has positive reduction potential. The species lying below it is having negative reduction potential. Okay. Hope this is clear to you. So you can just look at this data. Okay. Now if you look at the substance which is having negative reduction potential, lithium plus, sodium plus, Mg2 plus, Al3 plus. Okay. Now if you look at them, okay, if lithium plus, if we talk about reduction potential of lithium plus, sodium plus, or magnesium 2 plus, or aluminum 3 plus. So when they are undergoing reduction, they will change into metal. Okay, lithium plus will form lithium, sodium plus will form sodium, magnesium 2 plus will form magnesium, Al3 plus would form aluminum. Now we know that these metals are highly electropositive in nature. So their tendency is to oxidize. So as soon as they are formed, their tendency will be to get oxidized. So we will say that their tendency to get reduced is very less, because they will try to be in the cationic form only, because the metal is highly electropositive. So as the metal is exposed in the air or it is taken in the solution, they will generally have the tendency to get oxidized. So they will try to remain in the aqueous solution in the cationic form. So we will say that their reduction potential is negative. Similar is for zinc 2 plus, okay, similar is for iron 2 plus, similar is for cadmium 2 plus, similar is for nickel 2 plus, similarly is for Pb2 plus. Okay. So this data you have to observe. Okay, you have to observe this data. Like we will try to remember few of the data. Okay, but that would happen with time only. I will not give you anything to memorize right now. So we will be just focusing on the conceptual portion. Okay, with time we will eventually start learning few of the important data. Okay, so if you look above, okay, so tin 4 plus changing into tin 2 plus is again having a positive oxidation state. Copper 2 plus taking up 2 electron changing into copper is again 0.34 volt. Okay. Similarly, iodine changing into iodide ion is 0.54. Silver ion taking up electrons and changing into silver is 0.8 volts. Okay, and so on and so forth. So this is your basic, okay, electrochemical series or the activity series. Okay, hope this is clear to you. Okay. Now let us understand the concept of electrochemical cell. So basically an electrochemical cell is a device that is used to convert chemical energy in a redox reaction into a electrical energy. Okay, obviously the reaction has to be a spontaneous one. So electrochemical cell basically converts the electrical energy of a spontaneous redox reaction into electrical energy. Okay, so they are also called as galvanic cells or voltaic cells. Okay, so let me draw the basic setup to make you understand how this electrochemical cell works. So basically in the cell you will have always two electrodes. One is called as the cathode and the other electrode is called as the anode. Now we will not remember conventionally according to the sign, because in galvanic cell and in the electrolytic cell the sign of the cathode and anode is opposite. So we will just understand the electrode through the reactions which is happening at those electrodes. Okay, so cathode is the electrode where reduction occurs. Okay, so this is universally true, because if you look at the cathode charge, if you look at the electrolytic cell, okay, so we say that in electrolytic cell cathode is the electrode where cations migrate. Okay, cations come toward cathode. Okay, so cathode must be having negative charge, whereas in the electrolytic cell anions migrate towards anode. Okay, because anion is having negative charge, it is migrating towards anode. That means anode must have a positive charge. So that is true in the electrolytic cell, but that is not true in the electrochemical or the galvanic cell. Okay, the sign on the electrode is opposite. In this case, cathode is positive and anode is negative. So we are not going to define it according to the charges on the electrode. We are basically going to define it through the reactions that are going at that particular electrode. So cathode is an electrode where generally reduction occurs, and anode is the electrode where oxidation occurs. So you have to just remember this. Anode is the one where oxidation occurs. Cathode is the electrode where reduction occurs. Okay. So let me construct a galvanic cell, okay, to understand how a galvanic cell is working. Okay. So let me take a zinc rod dipped in a zinc sulfate solution. Okay. So suppose we are taking okay, so this is suppose your zinc sulfate solution. Okay, this is our zinc sulfate solution. So this is our zinc sulfate solution. Okay, we are dipping a zinc rod in this solution. Okay, so what we are doing, we are dipping a zinc rod into a zinc sulfate solution. Okay, so let me just sketch it properly. Okay, so we have taken a zinc rod dipped in the zinc sulfate solution. Okay, similarly we take a copper rod dipped in the copper sulfate solution. Okay, so this is your copper sulfate solution. Okay, we are dipping a copper rod in it. Okay, just draw it properly, because if you are clear with the setup, if you have understand the setup, how things are operating over here, and if you are clear how we are drawing and how we are representing a cell, then things would become much more easy, okay, to understand and to solve. Okay, so we have taken a copper rod and we have dipped in the copper sulfate solution. Okay, now we know some of the thermodynamic data. So in this case we know that the reduction potential of zinc is minus 0.76 volt and the reduction potential of copper 2 plus is 0.34 volt. Okay, so this data is known to us. Now we can see that the reduction potential of copper 2 plus is positive, whereas reduction potential of zinc 2 plus is negative. So we can clearly make out that copper 2 plus would be reducing in this case. Okay, it will undergo reduction and it will change into copper, whereas zinc would undergo oxidation, because its oxidation potential would be positive. So when you have taken zinc rod dipped into the zinc sulfate solution, okay, so basically the oxidation of zinc would be happening, and if you have dipped copper in the copper sulfate solution, so you can see that the reduction potential of copper 2 plus is positive, whereas the oxidation potential of copper would be negative. So in this case the reduction of copper 2 plus would take place. So what we will do is, in one half oxidation would be going and in the other half a reduction would be going. Okay, so we know that the oxidation is loss of electron. So when this loses the electron, we connect the two rods with a conducting wire so that the flow of electrons starts. Okay, so this is the main concept of galvanic cell. Now what you could have done is, you could have taken copper sulfate solution and you could have dropped a zinc rod on it. Okay, so you had have taken a copper sulfate solution and dipped a zinc rod on it. So in this case, zinc would undergo oxidation. Okay, zinc would change into zinc 2 plus ion, and the copper 2 plus ion in the solution would come on the rod and get deposited as copper because its reduction potential is positive. But in that case, everything is happening inside the solution. There is no movement of electron which we can capture. So if we can separate the two process, and if we can see the electron movement, if we can cause that electron to move from the solution through a conducting wire into another solution, so we will get the flow of the current, okay, and from this we can extract electrical current. So what we are doing, we were just doing a redox reaction. We are separating the two redox reaction or the two half reactions, and we are connecting them through a conducting wire so that the flow of electron could be observed. Now if the electron is flowing, so we can use them as the current, okay, source of current. So in this case, what would be happening? We know that zinc would be oxidizing. So in this case, zinc would keep on, okay, oxidizing, because we know that the oxidation potential of zinc is positive. So the tendency of zinc to get oxidized is more than that of zinc 2 plus getting reduced. So zinc would keep on oxidizing, okay, so it would undergo oxidation. So so some portion of the rod, okay, would start decaying, or we will say that the zinc that is present on the rod would enter into the solution as zinc 2 plus ion, and the zinc in the rod would be decreasing. So after some time, what would happen? Zinc is getting oxidized, okay, so zinc will get oxidized, it will change into zinc 2 plus ion, and the electron will go on the remain on the rod, okay. So zinc 2 plus goes into the solution, the electron remains on the rod. Now this electron can move through this conducting wire into the other half of the cell, okay. So what happens over here is, okay, on oxidation zinc is changing into zinc 2 plus. So after every time zinc 2 plus is added in the solution, okay, and the electron which is liberated out is getting, okay, is on the rod which is connected through a conducting wire to the other half of the cell, okay. So this electron passes to the cathode, okay, or to the copper cell, okay. So we'll say that zinc is continuously oxidizing. So we'll say that zinc is changing into zinc 2 plus, okay. The zinc 2 plus will pass into the solution, the electrons would remain on the rod, okay. So after some time, what would happen? More and more zinc 2 plus would keep on going into the solution. So after some time, this solution will acquire a lot of positive charge, okay. So this solution will acquire a lot of positive charge. So what will happen? They will repel the incoming zinc 2 plus, okay. So when you are dipping a zinc into the zinc solution, okay, zinc ion solution, so zinc is getting oxidized, so it will get converted into zinc 2 plus and it will enter into the solution. So this zinc 2 plus will keep on going into the solution. After some time, the solution would acquire excess positive charge. Now due to this excess positive charge present in the solution, it would not allow zinc 2 plus to come into the solution from the rod, because if further zinc 2 plus is coming from the rod, they would get repelled from the solution, okay, because solution has acquired excess positive charge due to the presence of zinc 2 plus ion. Any zinc which is oxidizing now, changing into zinc 2 plus, but that zinc 2 plus cannot enter into the solution because it is having a positive charge and the solution is also having the excess positive charge. So after some time, this oxidation would stop, okay. So this electron goes and come in the, okay, come in this segment, come in this half. So this electron through the copper wire can enter into the solution. Now we know that the reduction potential of copper 2 plus is positive, okay. So copper 2 plus in the solution takes up these electron coming from the other half, okay, and changes into copper, okay. So what happens here? The copper 2 plus takes up the electron and it changes into copper, okay, and it starts getting depositing, it starts getting deposited at the electrode, okay. Hope this is clear to you. So what happens over here is, we know that this solution is having copper sulfate. So suppose there are 10 copper 2 plus ion and 10 sulfate ion. So out of 10 copper 2 plus, some copper 2 plus would get reduced and get deposited as copper metal on the rod. So the solution will have more negative charge because some copper 2 plus has been now reduced into copper. So the solution will acquire negative charge. So after some time, what will happen? Excess negative charge would be present in this solution. Okay, so any incoming electron would get repelled. Okay, so any incoming electron would get repelled from the excess negative charge that is created in the solution. So this electron cannot flow and come into this half side. Okay, so we'll say that reduction also stops and the flow of current also stops. So this is not the complete cell now. The cell needed to be completed. Okay, so we introduce a concept of salt bridge. Okay, so let us understand first. So we'll say that this half is known as anode. Okay, because at this half oxidation is happening. Okay, this half is known as cathode because reduction is happening over here. Now you can see that in the cathode, okay, the oxidation takes place and the rod has a electron, so the rod acquires a negative charge. So anode is also the negative terminal, okay, and cathode, because copper 2 plus is depositing at the electrode, so we'll say that cathode is positively charged in this case. Okay, so let me just quickly make you understand this. Okay, so when we are taking zinc dipped in a zinc 2 plus solution, so zinc has the tendency to get oxidized, so zinc will keep on oxidizing. Okay, so zinc will keep on changing into zinc 2 plus. Okay, so this zinc 2 plus will enter into the solution. So zinc 2 plus will keep on entering into the solution. So due to this solution will have excess positive charge and the electrons which is getting released would be there on the rod. Okay, and this electron can flow from anode to cathode through a conducting wire, okay, that we have connected from anode to cathode. So after some time, what happens is there is a lot of zinc 2 plus that is developed in this solution. So this stops the further oxidation because there is already excess positive charge in the solution. Any zinc which oxidizes into zinc 2 plus, but that zinc 2 plus cannot enter into the solution as there is already excess positive charge in the solution. So oxidation stops. Okay, now this electron goes in the cathodic half. Okay, so this electron is taken up by the copper 2 plus in the solution because the reduction potential of copper 2 plus is positive. So copper 2 plus reduces and changes into copper. So copper 2 plus from the solution gets reduced into the copper and this gets deposited as the copper on the copper rod. Okay, so the number of copper 2 plus ions in the aqueous solution will decrease. Okay, that would lead to the negative charge development in the solution because initially there was equal number of copper 2 plus and sulfate ion. Now some copper 2 plus has gone from the solution and changed into the solid copper. Okay, so the solution will have negative charge. Okay, the solution will keep on increasing the negative charge now, which will repel this incoming electron. So this electron cannot come inside, so reduction would also stop. So after some time, okay, zinc is getting oxidized, the electrons would be going to the cathode, reduction is happening of copper 2 plus, but after some time this flow of electron would also stop. So to complete the circuit or to neutralize these excess charges, we need to have a salt bridge. Okay, so salt bridge is basically a inverted, salt bridge is basically a inverted glass U tube. Okay, so this is U shaped having, okay, this has some, okay, so this is basically having some gel. Okay, so this is agar gel, okay, or gelatin. Okay, so it is having agar gel or gelatin. Okay, and it has some suspended electrolyte. Okay, so the common electrolyte that is present in them is KNO3, NH4NO3, okay, etc. and so on and so forth. Okay, we'll discuss this in the upcoming class also, so don't worry. So we are saying that we are having excess positive charge and excess negative charge in the anodic portion and in the cathodic portion. Now each of them are called as half cell. This is one half cell which is anode half cell, and this is one half cell which is cathode half cell. We combine anode and cathode half cell to get a complete cell. Okay. Now the process was not complete because there was a development of excess positive charge over here and there was a development of excess negative charge over here. Okay. So what we do is we connect them with a U-shaped, okay, we connect them with a U-shaped salt bridge. So this is called as a salt bridge. Okay. So the one that is shown in green is a salt bridge. So salt bridge is basically having a agar-agar or a gelatin gel in which electrolytes like KNO3 and NH4NO3 is suspended. So what this salt bridge does is, we know that we have created some excess positive charge over here. So this salt bridge pumps out some anion. Okay. So it will pump out, say KCl is there. So it will pump out Cl negative in this segment because it is having excess positive charge. So this Cl negative will neutralize the excess positive charge. Similarly, we know that there is excess negative charge over here. So this salt bridge will pump some potassium into this solution. Okay. So when this pumps out some potassium in this solution, so the excess negative charge or the excess sulfate ion which was present over there gets neutralized. So in this way both the solution gets neutralized. Okay. Now if the solution gets neutralized, so again this oxidation will start happening, zinc will change into zinc 2 plus, electron will be liberated which will go to the cathode. Okay, and through this cathode it will enter into the solution, copper 2 plus will get reduced. Okay, again, so the flow of the current keeps on going. So salt bridge basically completes the circuit. The external circuit was connected through a connecting wire and the internal circuit is complete through salt bridge. Okay, so salt bridge is basically a U-shaped inverted tube and it is having a porous opening. So this is not a complete opening. So this is having a porous opening. So ions diffuse from this side. Okay, the ions in this cathode half and the ion in the anode half does not enter into this. Okay, so this is only the potassium or the chloride ion or the potassium or the nitrate ion can be pumped out. So no copper 2 plus or sulfate ion can enter into this, no zinc 2 plus and sulfate ion can enter into this. Okay, so this basically pumps out the charges and neutralizes the excess positive and negative charge. That also completes the internal circuit because the charges are moving, so this will also complete the internal circuit. Okay, so this is how you construct a complete cell. Okay, so let me just revisit in 5 minutes so that you get to understand about it. We will discuss the galvanic cell. I will show some model on this as well. So we are saying that this is basically an example of a Daniell cell. Okay, so we have taken a anode. Now we are describing in terms of the technicalities involved. So we know that the cell is always have a anode and it will always have a cathode. Anode is the segment where oxidation occurs. Cathode is the segment where the reduction occurs. So this portion is known as anodic half cell. This portion is known as cathodic half cell. The full cell is made by connecting them. So when you take a metal rod dipped in its aqueous solution, okay, so zinc dipped in zinc 2 plus ion. So we know that zinc will get oxidized because it has more oxidation potential. So zinc will get oxidized. So zinc 2 plus will keep on entering the solution from the rod, okay, due to which the solution will have excess positive charge. The electron which is liberated will be on the rod, okay, which can enter into the cathodic half cell through a conducting wire. Okay. Now this electron enters into the cathode, so it reduces the copper 2 plus present in the solution. Okay, copper 2 plus gets reduced into copper and gets deposited at the copper electrode, due to which copper 2 plus would disappear from the solution. The solution will have more number of sulfate ion. Due to this solution acquires excess negative charge. Now due to this excess negative charge, the incoming electron would be repelled and reduction of copper 2 plus would be stopped. Similarly, when there is a excess development of positive charge in this solution, it will repel the incoming zinc 2 plus coming from the rod. So the oxidation of zinc would also stop. So this cell would be incomplete. So to complete the cell, we are introducing a salt bridge. So salt bridge is basically a U-shaped inverted tube, okay, that has a gel suspended with a gel, agar or gelatin is the gel, okay, in which some electrolytes are present. Electrolytes like KCl, KNO3 and NH4NO3 is present. So when you connect them, they have a porous opening, okay. So through this porous opening, only the ions can move from here to here, okay, from the salt bridge to the solution, okay. So these ions in the cathodic half cannot enter into the, okay, cannot enter into the salt bridge and come over here, okay. Similarly, the ions which are present over here cannot enter into the salt bridge and enter into the cathode. So we say that the excess positive charge is neutralized by this, okay, salt bridge. It pumps out some negative charge in this solution so that the positive charge get neutralized, and similarly because there is excess negative charge over here, so this salt bridge pumps some cation into the solution so that the negative charge is also neutralized. So this completes the circuit, okay. The electron, the cation and anions are moving from here, so this also constitutes the flow of, okay, electron or the flow of charge. So we'll say that both cathodic and anodic half are neutralized. Again the oxidation starts, so again the electron moves, reduction again starts, so the electrons start moving, and due to the pumping of the electron, the internal circuit is also complete. So this is how, okay, we say that a galvanic cell is working, okay. Hope this is clear to you, okay. So this is the basic working of a galvanic cell. This is also known as a Daniel cell, okay. So this is it. We will discuss in detail about the salt bridge, the purpose of salt bridge, okay, and again we will study some parameters about the Daniel cell, okay. We will find out the overall EMF, we will find out the Gibbs free energy of the cell, we will check which cell is spontaneous, which is not, we will solve some question, and then we have to enter into the second portion of this chapter, that is types of electrode. So I hope you have understood the chapter till now, okay. So I hope you have understood the concept which was given today. So for better understanding or for having a better view on this, you can obviously undergo some theoretical reading, you can read NCERT, okay. So this is it for today. I will be again like demonstrating this chapter on Thursday. So we'll catch on Thursday, okay, for more detailed application of galvanic cell. Thank you, students.